let's get started here. Before I get started, I'd like to thank OWASP, and I'm very proud to be a longstanding member of OWASP. It's a great organization. Thank you to the OWASP programming team, Mark Miller, and the rest of the folks that are facilitating this today. Thank you very much for inviting me. My session is going to be on security chaos engineering and how it can help turn the tide in a war on uncertainty and how we build modern software. So, and especially how we secure that modern software. So right at the bottom, you'll see my Twitter information at Aaron Rinehart. Please feel free to DM me anytime. My DMs are open. All right, so I'm going to talk a little bit about what is chaos engineering. I'm going to explain what its applications to cybersecurity are and how to do that. I'm going to talk a bit about also complexity in modern software. I'm going to talk about the use cases you can use chaos engineering for security. We're going to talk about a light experiment framework, and I'll give you an example of security chaos engineering experiment. So let's get started here. Okay. Oh yeah, here's my background. So I'm the former chief of security architect at United Health Group. Currently I'm the CTO at Verica.io. I started Verica with Casey Rosenthal, the creator of Chaos Engineering at Netflix. He is my co-founder. I'm a frequent speaker and author on the domains of chaos engineering and security. I'm the O'Reilly. I recently wrote the O'Reilly book on security chaos engineering with Kelly Shortridge, and we're actually writing the larger book now. But I also helped write the main body of knowledge for chaos engineering with Casey. And let's get started. Let's go. The issue that we're trying to combat with chaos engineering, especially for security, is we don't seem to be outages, breaches, and incidents seem to be happening more and more often. They seem to be getting larger, and either way, from a grade or a score, a scorecard, we don't seem to be getting much better at what we're doing. Why is this? I'll give you some of my theses and what I believe why this is happening, and what I think we might be doing wrong. The problem is one of complexity, is that our systems have evolved beyond our human ability to mentally model their behavior. Because of the size, scale, speed, and complexity of modern software, things like the public cloud. Once you start adopting like the public cloud, DevOps, CI/CD practices, adopting the microservice architecture models, our systems just are moving at such a pace. And that the scale they operate is like nothing we've ever seen before. And it's very difficult for us as humans to mentally model what's going on in that post-deployment world. So chaos engineering and security, its applications to security, are really what we're not really targeting the sort of the build process with our experiments. It's the post-deployment world that is becoming overly complex. And I'll explain more about that here in a minute. But I just want to draw your attention to this little diagram. On the left-hand side of the slide, you'll see a bunch of dots that are connected. Each dot represents a microservice. Okay, what's happening is that like when you have like a system with 10 microservices, you don't actually have 10 of them. You may have, first and foremost, you may have a different group of humans working on each microservice. You probably have at least 3 or 4 microservices, 3 or 4 of each microservice running for throughput reasons. On top of that, you might have older versions running to support other functionality and other services, because microservices, believe it or not, are not independent, they're dependent. So what happens is you may have, at the gate, you may have, I don't know, 5 to 10 to 15 of each service, because you also may be doing blue-green deployments and testing out new functionality in some services. So it gets really complex really quickly. The problem is there's no group of humans anywhere in that model has a really good understanding of what the system looks like post-deployment. And it's hard for us humans to model that in our brains, because we need to abstract and simplify. So, but this is the crux of the problem, is the complexity is magnifying because of speed and scale. So where does the complexity come from? Well, there are a couple different schools of thought here, but there's essential complexity comes from things like Conway's law. So the way that organizations design, the way that basically Conway's law states that organizations are destined to design computer systems reflect the way they communicate as a business. that you can't really change that complexity that comes from that venue, from that avenue, without changing the business itself. The other is accidental complexity, the way and methodologies and the way we build software. But the problem with software is that it only increases in complexity. So, but all these other techniques you're seeing on here, like you see DevOps, you see continuous integration, you see cloud computing, service meshes, microservices, auto scaling, circuit breaker patterns. You're like, Aaron, these are all things that help us deliver value to market much faster. Yes, but they also increases our ability to scale and to change things quickly, which also is inherently related to complexity. And we'll talk more about this as we go on. So, newsflash, I love this slide. The new OSI model is software. Pretty much layer 2 and above is pretty much all software now. And it officially has taken over. The problem with that is it only ever increases in complexity. So let's say you have a complex software system, right? And say you wanted to make it simple. Well, there's a relationship between changing something and making it more complex. The more you change, the more complexity you add. If you wanted to make a complex system simple, you have to change it to do that, right? So you're not actually simplifying. You're just moving complexity around. So chaos engineering, what we're going to talk about is it's about navigating the complexity. It's not about trying to simplify it. So, and that's really what we're trying to do here. So chaos engineering allows us to ensure that the system is actually reflecting what it actually exhibits the characteristics that we believe that we designed it to initially operate under. So a good example would be is every company has a legacy system, right? Some of the characteristics for legacy systems could be that they're mostly known for being stable. Engineers are somewhat confident and competent on how to operate the system. It rarely has outages or incidents or issues, but it's legacy because it's business critical, right? I mean, if we want to, we would get rid of it if it wasn't, right? Well, the question I formed in my mind a few years ago is like, was the legacy system always so stable? Well, they weren't, right? Is the answer, is that we slowly learned about how the system actually worked versus how we thought it worked through a series of unforeseen events, surprises. There were surprises because we would have known surprises means incidents and outages. If they weren't surprises, we would have just fixed them, right? Learning about how the system actually works versus how we thought it works through incidents and outages is a very expensive and counterproductive exercise. Yes, slowly we learned that the system worked a different way than we thought. We were able to fix it, recalibrate it, and over time we developed a better understanding. But that process encountered a lot of pain for customers, a lot of pain for the engineers. So what you can think about is chaos engineering. Chaos engineering is a proactive exercise of introducing, so it's a proactive exercise of introducing turbulent conditions into a system or service and try to understand the conditions by which it will fail before it actually fails. And so what's great about chaos engineering is we're not actually causing chaos. What we're trying to do is proactively ensure that the system can actually do what it's supposed to do under the conditions we design it for. If you think about things like failover logic or circuit breakers or failures or circuit breakers, even security controls, those code paths rarely ever get exercised until they're actually needed. And when they're needed, it's usually some sort of catastrophic event. The problem is that our systems, the rest of the system has changed a lot since we originally designed those code paths, and those code paths might not work the way we think they're supposed to work when we need them. Same thing with security. We often build detection and prevention types of controls and capabilities under a certain context and understanding, but the system often changes a lot before those controls actually come into use. So what we're trying to do is proactively ensure the system still does the things it's supposed to, instead of learning that we didn't understand the system through an outage or a security incident. Part of this problem is that system engineering is a messy exercise. Okay, in the beginning, we love to think the system is very simple, right? We've got a plan, we've got our time, we got the resources, we got the engineering team put together, we've got our Docker images, our secrets taken care of. We got our different environments. And of course, we have a beautiful 3D AWS diagram. Well, in reality, our system never looks like this, okay? It's because after a few weeks, after a few months, we start learning about what we didn't actually know about the system, right? After the first week, there's an outage on the payments API, so we have to hard code a token. Marketing team comes down and says we have to refactor the pricing modules. We refactor, right? And we go from incident to incident to incident. But what these incidents are informing us is that difference between how we thought the system worked and how it actually worked. And then over time, it just continues to magnify. And our system, what Sidney Dekker calls this, he's one of the world's experts in complex systems in terms of safety engineering. He likes to call this the drift into failure, the drift into the unknown in a complex system. So in the end, the summary is that our systems have become more complex and messy than we originally remember them being. All right, so what does all this have to do with security? I'm getting there. Okay. So security is a context-dependent discipline. So what I mean by that is that, so I've been a builder most of my career, a software engineer predominantly most of my career before I got into security. And so as an engineer, I need the flexibility and convenience to change something. That's my job. I'm constantly trying to change something because I'm trying to deliver value to market via product, delivery to customer, right? So I'm constantly trying to deliver on that promise, so I'm constantly building and delivering that value. But security is a context-dependent discipline. You need to know what you're trying to secure in order to know what needs to be secured about it. So we're kind of forced into a stateful understanding of a thing in order to actually manifest the security. What happens is that what's happening is we're starting to see a drift issue between the rate of change of the actual system and the security being able to maintain alignment with its original context and understanding. With chaos engineering, especially for security, we're introducing the conditions that our controls were originally designed for to make sure that we can catch the drift out of effectiveness of the control before an adversary can take advantage of the fact that we didn't realize that the security control needed recalibration, so that's kind of the crux here. Chaos engineering. So in terms of like instrumentation for software, Casey and I like to sort of refer to break them down into sort of two domains. There's testing and there's experimentation. So testing is the verification or validation of something you already know to be true or false. You know what you're looking for before you go looking for it. In our world, that's like a CVE, that's an attack pattern, that's a signature, things like that. Where experimentation, we're trying to derive new information that we previously did not know. And this is where chaos engineering fits in. We're not trying to do a simple test. What we're trying to do is experiment, and I'm trying to generate new context and understanding about how the system is operating post-deployment. So how do we typically discover when our security measures fail? Well, it's typically through some sort of footstep in the sand, some observable event, some context the computer tells us, meaning it could be a log event, it could be an alert, it could be, and usually the problem is that we often only discover that our security measures were not effective when there's a security incident. But unfortunately, security incidents are not an effective measure of detection because it's often too late. So what happens during a security incident? Okay, well, in shorthand, people freak out, and this is not a good learning environment especially for the engineers, right? So we don't do chaos engineering here, right? When there's an active incident or an issue. We do chaos engineering when there is no problem, to proactively understand, so we don't end up in this situation. We do it here, right? We proactively try to build an understanding about whether or not the security still does what it's supposed to do before we run into situations where we're freaking out. It'll make more sense when I go through a couple examples. So chaos engineering. So the Netflix definition of chaos engineering was the discipline of experimentation on distributed systems where to build confidence in a system's ability to withstand turbulent conditions. Or like I said before, it's the practice of proactively introducing failure conditions or faults into a system or service to try to understand the conditions by which the system or service will fail before it actually fails. Instead of chasing outages, we're proactively just ensuring the system does what it was originally designed to do. So chaos engineering, very important. It's not about breaking things in production. It's not about breaking things. Don't go back to your job at work and say you want to do chaos engineering to break stuff, I'm pretty sure you get fired. So it's about proactively fixing things. We're trying to fix things, right? We're an established order, not create chaos. So there's several books on chaos engineering. I mentioned a couple of them earlier. Actually, there'll be links to download them. I highly recommend you download them both now if you're watching this, because I'm not sure. I think both of these I think will expire soon on the free download. You can only sponsor the book forever. You can't sponsor it forever. So I highly recommend you go get that book. The links will be at the end. So security chaos engineering. Well, newsflash, it's not a whole lot different than chaos engineering. And so before I sort of explain security chaos engineering, I want to remind everyone of how I see software engineering is that engineers don't believe, well, we don't believe in two things. We don't believe in hope and luck. I mean, we believe in good instrumentation, data, and feedback loops. That's what we believe in. I mean, hope and luck, it worked in Star Wars, but it doesn't really work in engineering. Okay, what we're trying to establish with security chaos engineering is understand, excuse me, where our security gaps and needs for recalibration are before an adversary can take advantage of them. So a use case that I like to talk about for security chaos engineering will be incident response. I'm going to cover a few other use cases as well, but the main problem with incident response itself is that it's a response. So before I do that, I'm just going to explain a couple of the use cases you can use it for. You can use, by the way, all of these use cases are well documented in this book, and they're going to be expanded on the larger book. So you can dive into the detail later if you would like. Where I started with chaos engineering for security would be security control validation. I was trying, as the chief security architect, I wanted to ensure that post-deployment, the security mechanisms and controls and things like that were actually being implemented correctly. I mean, because configuration matters, how it's configured, how it's placed, how many of them, where they are, and there's too much subjective process in the assessment between me and the computer. I need to ask the computer a question, and instrumentation is a great way to do that. So I created a new methodology and a new open source tool that actually allowed me to do that. I'll explain that in a minute. Another great use case is security observability. It's one of the biggest problems in software security, in my opinion, is that it helps you because you're proactively introducing conditions that security control should fire on. You actually you can get a better understanding of how of what did the log data make sense that you got from the control. If this were a real incident, do we have enough log information to correlate alerts? Did it correlate an alert? Did we understand what the alerts or did the SOC analyst understand the alerts and what to do with it? Another great use case is compliance. Every chaos experiment, whether it's availability or stability based or security based, has compliance values. So make sure you just keep the output in a high integrity way and label it with the right control framework. So back to incident response. So the problem with incident response is the response, and security incidents are somewhat subjective. No matter how much money you spend, how many people you have in security, but you still don't know a lot of things. You don't know where it's going to happen, why it's happening, who's trying to get in, how they're going to get in, and what they're trying to achieve, right? But what's great about chaos engineering is we're proactively introducing the conditions ourselves. It's managed, right? We're introducing a misconfiguration of some kind, and we can watch it because now we're not waiting for something to happen and try to figure out if we were prepared or not, because that's a very subjective way of doing it. What we're doing is introducing a objective signal into the system and watching it. So, when we start introducing these experiments, we can now, because we know the point it started, right? So we can look to see whether the technology was effective at doing what it's supposed to do. We can manage and measure things like, were the runbooks correct? Did we have enough people on call? Did they know what to do? Did we follow the process correctly? That could be a great and highly valuable feedback for sharpening the incident response process. So Chaos Slinger. Chaos Slinger was the first ever application of Netflix's chaos engineering to cybersecurity. It is now a deprecated tool out there on GitHub, but it represents a framework on actually how to write security chaos experiments through a series of Python-based lambdas. and it's fairly easy to understand the framework if you check it out. It's also documented in the O'Reilly report. So the main example when we open source Chaos Slinger was we wrote several experiments for Chaos Slinger, but one of the main examples, we needed an example that a lot of, whether you're a software engineer, a network engineer, a systems engineer, an executive, that you could understand what we're trying to do and the value we're trying to achieve. And for some odd reason, misconfigured or unauthorized port changes still happen a lot of the time, even in the cloud. So what we did was, United Health Group, when I was there, we were very new to the AWS, and what we started doing is the assumption is that when we introduce a misconfigured or unauthorized port change into our AWS instances, we expected the firewall to immediately kind of detect and block that kind of activity and be a non-issue. So what we did is that we would pseudo-randomly select through a series of AWS tags. You can see how this works on the repo for Chaos Slinger on GitHub, but it'll select a series of tags to be opt-in or opt-out. If it's opted in, that means we're able to actually do the experiment on that instance, but we would open or close a port that wasn't already open or closed. What we're trying to do is sort of make sure that the firewall actually was detecting and preventing what we thought it was supposed to prevent and detect. What actually happened was, it only worked about 60% of the time, is that what we learned was actually there was a configuration drift issue between our non-commercial and our commercial software AWS environments. Easy. Remember, there was no incident, there was no war room, there was no, nobody's freaking out. We proactively realized we had a drift issue, we were able to fix it, right? So the second thing we learned is the cloud native configuration management tool caught the change and blocked it every time. So something we're barely paying for, we didn't even expect this to happen, caught it and blocked it every time. So that was very interesting to learn that. So the third thing we learned is we didn't really have a SIEM. We wrote our own sort of security big data lake solution. I did not have a whole lot of confidence that actually their alert would get generated from the logs that came from the controls. It actually did. According to the alert went to the SOC. The problem is that when the SOC got the alert, they couldn't tell which AWS environment came from. As an engineer, you're saying, oh, Aaron, I can map back the IP address and forgot where it came from. Yeah, you can, but that could take 15 to 20 minutes maybe. Or it could take an hour if SNAT is in play, because SNAT intentionally hides the real IP address. So you could, that's a long time to be, especially if that's an outage. Okay, but here's the great thing. There was no outage. Remember, nobody freaked out because we were being proactive, and we did discover this, that all we had to do was add metadata to the alert, and it's the problem solved. So that's kind of the value in doing some of this. You can find more about this, like I said, in the O'Reilly report. You can actually download that report at this link and download both books. Here are the links to both. I hope you enjoyed my presentation. It's somewhat a brief presentation on security chaos engineering. But like I said, you can find more on both of these resources about it. Thank you.